Commutativity, necessary for identity elements. Let's look at some definitions. A binary operation is a rule which at any instance of time combines exactly two objects of a set to produce a third object. We say a binary operation star is commutative on a set S if for any two objects A and B, A star B equals B star A. And here by objects, we are not limiting ourselves to only numbers. Numbers, of course, are the most fundamental mathematical objects, but they are not the only mathematical objects. Now, if there exists a unique element E of the set satisfying the equation A star E equals E star A equals A, where A is any member of the set, we say E is the identity element of the set with respect to the operation star, because E preserves the identity of all elements. Do we have a binary operation defined on scalars which is not commutative but has an identity element? By scalars, I mean real numbers. I have not encountered any such operation. Let me know if you have encountered one. Now, consider a binary operation star defined on the space of two-dimensional vectors as this: S star y equals this vector. Then the vector 2, 5 star the vector 3, 1 will give us the vector 5, 21. Now, if S star y is this, then y star x is this vector. If we inspect the two vectors carefully, we find that they are not equal. Their first components are equal, but their second components are not equal because the third terms here are not equal. y1, x2 is not equal to x1, y2. Therefore, star is not commutative. As an example, we find that the vector 3, 1 star the vector 2, 5 is equal to 5, 8. Meanwhile, we had 5, 21 when we performed 2, 5 star 3, 1. And so this is an instance illustrating the non-commutativity of star. Now, for any two-dimensional vector z with components z1, z2, we find that z star the vector 0, 0 produces the vector z, and the vector 0, 0 star z produces the vector z. Who behaves this way? Identity element. So the vector 0, 0 by this result is the identity element under star. So we have a non-commutative binary operation having an identity element. Second example, composition of functions. Let f and g be two functions of x. In general, we know that f composed with g is not equal to g composed with f. That is, composition is not commutative. Now define I of x to be equal to x. Then for any arbitrarily chosen function, say h of x, we have h composed with I equals H composed with X, giving us H. And also I composed with H, which is X composed with H, is equal to H. If you replace X by all of H of X, you will get H of X. Thus, the function I of X is the identity function with respect to composition of functions. So again, we have seen a non-commutative operation having an identity element. Final example, matrix multiplication. Let A and B be two matrices of order 2 by 2. Then we know that A times B is not equal to B times A. If I2 is the matrix 2 by 2 matrix with elements 1, 0, 0, 1, and C is any arbitrary matrix of order 2 by 2, we find that C times I2 equals I2 times C, which equals C. By this behavior, I2 is the identity matrix. So again, we have a non-commutative binary operation having an identity element. It is important for me to do a presentation like this because I once held the view that commutativity was necessary for the existence of an identity element. When I realized I held a wrong view, I apologized and continue to apologize to my past students and the readers of Thinking Mathematics. I would also like to share with you how I came to that false conclusion. I figured that I misinterpreted the definition of identity elements. That is, I inferred commutativity from the definition. The definition of identity element says A star E equals E star A. E is a special element. A is any element. So we are having this situation when we take any element and combine with that special element. Commutativity is saying A star B equals B star A for any two elements. This one says for any element and that special element. So this does not imply this.